écharpe de garde Meneau?
Non, à Paris, pour les
Ah oui,
gilets
pour
jaunes.
les gilets jaunes à la con.
Donc il y a tous les magasins des choses en bois, les vitrines et tout. Et tu vois, il y avait vraiment la guerre. Après les jouables, il n'est pas du tout là. Les jouables, tout est normal. C'est difficile parce que c'était pas, il essaie de faire un tout piéton. Mais en ville, c'est difficile à faire piéton. Tu dois comme ça, il y a des dents partout. Ils ferment tous les rues, tout bien, particulièrement des choses.
Oui, parce que c'est l'élection municipale qui arrive.
Oui, mais si tu réduis les parcours de voitures, c'est pas évident de se déplacer. En plus, il avait mis ses trottinettes, que c'est bien, ses trottinettes partout. J'étais comme des cadrans. Je pense que les idées sont pas dans cette porte. Et donc, c'est un peu...
So I'm sorry if I'm
It's working?
Can you please
Right. Hello and welcome everyone. Sorry for the delays due to technical issues. Welcome to the second press conference at the joint EPC-DPS meeting from here in Geneva. I'm Shantanu Naidu, the DPS press officer, and with us are Anita, Livia, and Adriana, who are the EPC-DPS press officers for this meeting. We had a slight change in the schedule. The OSIRIS-REx mission people had to withdraw their talks, but we still have 3 great talks today. First, we'll have Makoto Yoshikawa and Antonella Barucci talking about observations of Ryugu by the Hayabusa 2 mission, followed by Frank Marches from SETI Institute, who will talk about occultation observations of Orus, which is a Lucy's space mission target. So we'll have the 3 talks first, and then we'll take questions later. And also, I'd like to remind you to silent or switch off your cell phones. So take it over.
Okay.
Okay, hello everyone. My name is Makoto Yoshikawa, and me and Antonella Barucci will talk about the Hayabusa 2 mission. So first, my talk is the impact experiment and the second touchdown. Okay, at first, I show you this slide. This is a Hayabusa mission flow. So spacecraft, Hayabusa 2 spacecraft launched in 2014. And 1 year later, it came back to the Earth to perform Earthing by. And then Hayabusa 2 arrived at Ryugu June last year. And we had lots of observations. And last year in September, we released 2 small rovers, Minerva 2-1. And then October, we released a mascot, which was made by Diela and Knes. And the first touchdown was carried out in February in this year. And then in April, we did the impactor experiment to create the small crater on the surface of Ryugu. And the second touchdown was executed in July. So up to here, all the mission were finished, and they were all successful. And still, we have one more small rover, Minerva 2-2. We will release this in next month. And spacecraft will leave Ryugu at the end of this year, and at the next year, Earth return. So this is for our mission. And today I talk about the impact experiment and second touchdown. So last April, spacecraft went down to this altitude. This is about 500 meters from the surface of Ryugu. And it released small impactor we call SCI, small carry-on impactor. And this impactor went down slowly, but during that, spacecraft quickly moved from here to horizontally and then vertically, because the SCI explodes just 40 minutes later. So spacecraft must hide behind the asteroid. But if spacecraft is here, we cannot see the impact event. So before that, spacecraft release small camera we call DCAM-3, deployable camera here, and this camera observe the impact event. And then spacecraft go back to the home position. And next, we tried to do the second touchdown, not inside the crater created, but outside, but quite near to SCA crater, about 20 meters from the crater to get the subsurface material. Okay, so this is images. This is just after separation of SCI, like this. And after 40 minutes, it exploded, and we saw these ejector curtain from the surface of Ryugu. So impact experiment was successful. And later, spacecraft go back to the impact point, and we saw this one. This is before impact, after impact, and this is a comparison. So you can see clearly that there is a very big crater. The size is about 15 meters in width, and the depth is about 2 or 3 meters. So the size was quite large, much larger than we have expected. So next thing is to get the subsurface material. So we observed the region near this impact crater. And this figure shows the color change. The dark area means the change in reflectance before and after SCA impact. And this means that dark area means there is a subsurface material distributed. So if we go there, we can get the subsurface material. So we select this C01C area for the second touchdown place. And also we have spectral RAM data, near-infrared spectrum data for this impact crater. And the central figure shows the spectrum. This absorption means water, there is water. And this orange line is outside crater, and this blue one is inside crater. So the spectrum shape is quite similar outside and inside. But reflectance is smaller inside crater. Okay, so second touchdown, we studied a lot around the touchdown region because there are lots of boulders like this. And but anyway, we confirmed that we can do touchdown safely. And touchdown sequences like this. Spacecraft went down to about 30-meter altitude, and then hovering, and then again it went down to the 8.5 meter, and hovering, and touchdown. So this is a movie at the touchdown. This was taken by the small monitor camera, and the speed is 10 times faster than real motion, and touch like this. So lots of fragments were blown up. So we are sure that we can get the subsurface material. This is another photo at the second touchdown. And one more photo, this is quite interesting. This shows the impact crater by the wide-angle camera. This area is the impact crater, and this small dot, this is a target marker, which is an artificial landmark. We use this target marker to control the spacecraft. And this area, this point is Sampler Horn ground point. And finally, the accuracy of second touchdown is about 60 centimeter. The error is just 60 centimeter. So we were able to do the very accurate guidance. Okay, so this is a summary of my part. The impact experiment was successful, and we can make a large crater, larger than 10 meters, was created. The second touchdown was successfully executed at the surface about 20 meters from the SCA crater. And we think it is quite probable that the subsurface material were obtained. So this is my part, but I want to add one thing. This is quite a new thing. The operation just today, or in Geneva time yesterday, we did the target marker separation operation in Japanese time today, but time here is yesterday. And we released 2 target markers from altitude about 1 kilometer, and these images were just released. I mean, 2 hours before we released this image. So you can see target marker, image of target marker like this. So the purpose of this release is a rehearsal of the release of Minerva 2 small rover in next month. But we can observe target marker orbit around the Ryugu. Then we can able to determine the gravity field of Ryugu in detail. So this is a very new operation. Okay, so that is my part, and I switch to Antonella.
Okay, good morning, everybody. As you saw, the Ryugu is very dark object. And so when you see so dark objects, it's very difficult to understand the composition of the object. Looking the spectra, no spectra was similar to a meteorite. The meteorites were very different from the spectra of Bennu. And the more similar was like you can see in this plot was Ivuna or was CM meteorites, but was warmed meteorite or shocked, but the behavior is not really similar. So if you see, as Makoto told you, you see the feature at 2.72 micron, that is a feature of magnesium-rich phyllosilicate. That means something like serpentine or saponite. That means that water was there sometime during the formation of this object. So what we did, we were trying to analyze the complete object with a statistic. We use a multivariate statistic method that is very sophisticated and that has been used in the past for many planetary surface, really to understand the variation on the surface. So to do this, we apply on the camera data. The camera data, there was 7 filters that went from 400 nanometers to 950 nanometers. And the method allowed to have an automatic clustering with no a priori criteria and try to give a very different confidence level. So when you choose a confidence level very high, that means that you make a probability of wrong decision of only 0.3%. You have 2 groups. So one that is almost homogeneous, about 97% of the surface, and the other one here is in brown with a very blue spectrum that is 3% of the surface. And you see also differences on albedo. But when you go down in something smaller with a confidence level of 2 sigma, and which means that the probability of wrong decision is a little bit higher, you see much more classes. And so you can have a finer classification and see the small variation. And so you have something that is more redder in the spectra, something that is more bluer in the spectra, and this gives you some information on the composition. And in fact, when you look, the single pixel, you see that here, for example, you have the albedo, the reflectivity of the object. And here in this is Otaime Saxum, is a big boulder, 160 meters on the surface of Ryugu, and is completely different. It's much brighter than the rest of the surface. And also the spectra here is in red, is much more going down. And so you have a really completely different. So when you bring all these differences in a map, you can compare with the surface of Ryugu, and you see that near the equator, you see much brighter material, and this class is really much bluer, so we think that this is due to the space weathering. We have much younger surface around the equator. And this is also distributed around in the area. And we have analogy with, for example, in red we have the Ejima Saxum, or we have analogy with some boulder region. So this is very good because you have this variation, and these are connected with some specific craters or boulder. Or like, for example, here in green, you have the Cendrillon crater. So we did the same also with the spectra, even if, as you saw, the spectra was very thin variation. So we had to push the method to go to see much more. And here, if you see the same, when you go with a very deeper, smaller confidence level, you can have some variation. And these variations are real, because you have different in the slope, you have different in the spectral signature, and this is important. You see there are variations. These variations are real, and you see, for example, with the same code color, there is a variation on this slope of the spectra, on this band area of the spectra. So this means there is variation in composition, but this is also connected with the regolith size, because smaller is the regolith size, more you have redder the slope of the spectra. So I don't give all this detail, but I want to show that when you bring also this on the map of Ryugu, this was a map that was published by Sujita at the beginning of this year. You see there is really some differences on the spectra. There is a variation on the surface, particularly in this area where you have these classes that are represented in red, orange, and brown. So what is the conclusion of all this analysis? The conclusion is that it's true. Bennu is very homogeneous, dark. We don't see much stuff like variation. But when you go down with some statistical analysis and you decrease the confidence level, you see a lot of variation with different groups on the surface. So these variations are seen with the camera analysis, with the spectra data, and this has been due to the difference of hydrated silicate, even if the band is very small. This is due to the difference with some fresh material on the ridge, because the material was coming from the pole to the ridge. So we have a much more fresh material around here in some specific region. But then you have also some grain size different. And so all this is shown that there is a dichotomy on the object, and this dichotomy was already found with the analysis of geomorphology on the surface. So now we have this dichotomy that is also confirmed with the spectral analysis. So if you look at these objects, you know this is a rubble pile. Rubble pile means a reaggregate of material. So note all these results can give some constraint on the reaccumulation phases of this rubble pile. So this is very important. But all this is published on Astronomy Astrophysics, a paper that is just coming out. But we will have much more discovery with the analysis on the future of all this data that are huge quantity of data. We will have still more data with all this Minerva 2, all this new data that will arrive at least up to December, but we will have much more with the sample analysis when the sample will come back, because you don't have to forget that this is a sample return mission, and the sample will come back on end of 2020. So just at the end of next year. Sorry. And of course, I want to acknowledge all the team of Hayabusa 2 for this wonderful mission.
Okay. Good afternoon. So I'm here to talk about how you can do citizen astronomy and support NASA from your backyard using a new type of telescope, a digital telescope made by Unistellar. And I'm going to introduce first the concept of the Unistellar. So Unistellar EV-scope is a telescope you can see behind me here. It's a telescope that's been designed for everybody. It's a telescope which allows you to see galaxy nebulae in your backyard in color. He has electronics and sensors, so he allows you to see and to observe galaxy nebulae without knowing anything about the dark sky. Basically, it's kind of a robot, and it analyzes the sky, and from the location and the time of observation, it will give you a list of targets to observe. So that's the cool part of the project and the educative part of the project. You learn about astronomy by observing the dark sky. But we also started a collaboration a year ago with the SETI Institute, and the SETI Institute will use the sensitivity and the accuracy of the telescope to organize campaign of observation, transforming every Unistellar user into a citizen astronomer. So first, let me just show you what you can see with the telescope. This is what you have, you see with a normal telescope on the left, and that's what you can see with the Unistellar EV-scope. I remind you that we pre-sold already 2,500 of those telescopes, and the shipping has started. So this is becoming a reality, as you can see here. And if last night you attended our demo, you have seen the telescope in action as well. So we are now on the verge of starting science with this telescope, with this large array of telescopes. And one of the scientific investigations we prioritize is the study of asteroids using occultation events. So an occultation is simply if you are well located, you will be able to see the disappearance and appearance of a star because the asteroid is passing between you and the star. So as a user, if you are located nearby a path of this occultation, you will get on your phone an announcement telling you that you are close to a path of an occultation and asking you if you want to observe it. You set up the telescope in your backyard, you press a button, the telescope will basically move to the right position, start taking the observation, and hopefully will detect the occultation, the disappearance of the star and the reappearance of the star. The data will be sent to the SETI Institute and we will process the observation. So there is a lot of occultation that will be observable with this telescope, 40 per day. So to illustrate the capability of the telescope, we basically focus on one of them specifically that happened last Saturday. That's the occultation by the asteroid Horus. Horus is a Trojan asteroid, and it's a target of the Lucy mission that will be launched in 2021. And Horus will be visited by the Lucy mission, which will fly by the Horus asteroid. So we don't know much about this asteroid. We know roughly its size, we know its orbit. So observation of an occultation like this provide information about the size, the shape, if the asteroid has moons or not, and maybe more information, like maybe it could have rings, for instance. So we collaborated with Marc Bouy and at SWIRI and also Lucky Star at the Observatoire de Paris. And Marc sent us a prediction for this occultation. And what you can see at the bottom left here is the map of the occultation path. So this is roughly 50-kilometer diameter. And here we are basically in Oman. And this is the city of Khalil, if you like geography. So we sent a team over there with 2 telescopes. This is the Unistellar team. And we located a station across the central part of the occultation and one slightly offsetted, 30 kilometers away. And what you can see on the figure here, it's basically a movie of the occultation. You can see the star here disappearing. It's an accelerated movie. The disappearance lasted 4 seconds, 4.5 seconds roughly. So basically we capture the event. So what we see here is the disappearance of the star because of Horus passing nearby. And Horus is a faint asteroid, so you don't see Horus. You see only the stars being occulted by Horus. From this data, we can get an estimate of the size of Horus, which is 55 kilometers, which was what more or less what we expected based on additional data taken in the mid-infrared. We have now also some very interesting, we know now that this prediction path was extremely accurate. Mark basically used Gaia data, Penstar data to make this prediction. And we were basically observing at the center, and we caught the event. So it means that we are now ready for the next one. And the next one will be very soon. The next event will happen in November 4th of this year, and it will be visible in the northern part of Australia. So what you have on the left side here is the occultation event predicted before our positive occultation. As you can see, the band is now after slightly offsetting toward the north, and more importantly, the error on the band is much more reduced, because now from this observation we know precisely the position of Horus as well. So we are much more confident that we will capture an occultation if we are located across this 50-kilometer blue band here. So I know that the team at SWIRI is organizing a campaign of observation. They will basically go to Australia and use 20 small telescopes that will observe simultaneously the occultation to get this time not only one chord but multiple chords, and be able to see the shape of Horus and maybe detect the presence of moons around the asteroid. So this is important because thanks to those kind of observation, you can better plan the scientific flyby of Lucy. You can basically know where what you're gonna see in advance and start planning what can the process, the observing mode of the observation. As a user, as a unistellar user, using this telescope, you can now participate to large campaign of observations. You can become citizen astronomers and invest some of your time to help NASA to characterize asteroid from your backyard. Thank you.
Thank you, everyone. We'll take questions. Yes. Yeah.
Okay. Hello. Is it working? Okay. I'm Camille Carlisle. I'm with Skying Telescope. I have several questions, but let's start with two. For the surprisingly large pit that you got on Ryugu, what does that tell you about composition, about structure that you did not know before? And also staying on that asteroid, why would material be moving from the poles to the equator?
Okay. So first is that we know before that this was a very dark object, similar to carbonaceous chondrite from the observation from the ground, but we didn't have information on details. We didn't have the information of this signature at 2.72. So this feature is very important for the water content, for what we call a phyllosilicate. But it was a very thin one, was very small. So if you look here, these were the observation in gray. This part in gray was the observation we did at the ESO, European South Observatory. We see that the spectrum was very flat, so it was typical for carbonaceous chondrite. But we didn't have information on the composition. So here in black, you had the spectrum of NIRS 3, and you had this very small signature that is typical of magnesium-rich phyllosilicate. This is like serpentine or saponite. The problem, as you see, is so thin that when you compare with all the other meteorites, doesn't fit very well. So one of the work that was done by the Japanese colleague was to compare, and this is published in the Kita Zato paper on Science, was to compare with some warmed meteorite at higher temperature, like, for example, Ivuna, that is CI meteorites, or the shocked CM meteorite. And so you have a similar trend. But of course, it's difficult because you have all is included and mixed together. So the real composition, the real components will be when we will analyze back the sample in the ground.
But just to clarify, I was asking specifically about what you saw, that like why the impact created such a large hole, and what that
okay.
tells you.
Yes, okay. So this is a very good question, and actually, before this impact experiment, we thought the size of crater maybe just 2 or 3 meters in diameter, but in fact, the crater size is larger than 10 meters, maybe 15 meters in width. So actually, we were surprised to see this, and so now. The project member is studying this in detail, and I think soon we can publish the paper. But simply speaking, the gravity is very small, so. And the surface material is not so hard. So that's why we can the crater size becomes very big.
So it's the density
Yes, density is
and
small.
the porosity.
So it's more It's more porous than you thought it was.
Yes, you are right.
Okay.
Mhm.
Karl Urban, I am. Is it working? Yeah? Okay. Karl Urban, I'm freelancer for Deutschlandfunk, German Public Radio. I have also 2 questions concerning Ryugu. So I was surprised by the color in the inside of the crater. So why is it darker in the inside, or is it just a shadow effect on this very last picture? And the second question, what did you learn from this impact experiment in terms of planetary protection? So when a body like Ryugu would get close to Earth, which is possible, what did you learn from measures to defend against it? Thank you.
Do you have a comment about the color?
About colors, we saw that there is a much higher reflectivity, so it's darker. And so this is not only the shadow, as you say, it's a really different way to reflect the light. So this means that you can have also different grain sizes. It's very complicated because the reflection of the light depends on many parameters. So depend on the porosity, on the grain size, on the composition. So this is all connected together. But then what is one of the major results is that the porosity is very high of this object. So when you go back to the planetary defense, I think that such type of object are so fragile, so low density that when they have impact, we can lose this material depending on the way they impact the Earth, for example. So, of course, first, the impact depends on the composition. It's different if you have iron meteorite, iron body, iron asteroid, or carbonaceous chondrite object. And then depend on the inclination on which you have the collision, because if the direction is perpendicular, the impact is much more stronger than if the collision is at very low inclination. So all this are important parameters. I don't know if you want to add more about the impact lesson.
Yes. So I think this is very important. I mean, very important result for the planetary defense, because for this the impactor is very small, just a 2 kilogram copper. Okay, the size is like this, only like this. However, we can make such a big crater. We made a big crater. So maybe from now on we will study how much material was ejected to the planetary space. Then we can estimate the effect to, to change the orbit of asteroid. So I think this is very good data to study planetary defense. To change the orbit of asteroid by impact. So, okay.
Hello, my name is Hans-Arthur Mosiska. I'm from Germany, Verheise Online. I have two questions. One is quite easy, I think. I would like the price for the telescope. And the other is, on the picture, there is one boulder in the crater that seems to be uncovered from dust and seems to be, has moved after the impact, just one boulder. Is that a topic of special investigation?
Well, the price of the telescope is 3,000 euros on our website. 3,000. You can find it on our website. Yeah. Unistellar is a French company based in Marseille. So.
Okay, so your question is this border?
Yeah, exactly.
Yes, yes. So
that's the only one that seems to be moving. Yeah?
right. Yes, you're right. So for example, this border didn't move, but this one moves. So we think this border is much bigger to the vertical direction, but this one is only a what shall I say? Just put on the surface. So that's why this border is moving, and we think the impact point is around here. So this border goes, and this way. Mm.
More questions?
Hi, Luca Maltagliati from Nature Astronomy. I have two questions also for the two parts. Concerning the Hayabusa, now that you have the two samples, do you have an estimate of how much material you actually have? And for Frank, I wanted to ask first if you have other planned campaign for citizen science in addition to occultations, and what is actually the additional thing that the Unistellar brings, because of course you can have occultation observations with normal telescopes. So what was the the additional contribution that Unistellar can bring? For example, you can observe better occultations in more illuminated areas, or it's more sensitive to something, and so on. So.
Right. So first, for science cases with Unistellar, occultation is the first one. We can also detect asteroids as faint as magnitude 16. So we can do participate to planetary defense program as well. We can also detect exoplanet the size of Jupiter orbiting G-type star. We demonstrated this. So we can follow up tests and plateau in the future discovery to refine the orbit of those exoplanets, detect the presence of gravitational perturbation due to the presence of even smaller planet, or also help refining the orbit of those planets for JWST survey. So as a user you will be able to detect those exoplanets to kind of prepare for the next generation of NASA and ESA space telescopes. There is also a lot of different science cases that we are on the process of studying, such as detecting the afterglow of gamma ray burst, and also, why not, I work at SETI, so detecting the beam of laser communication from extraterrestrial species. It's possible that with this type of telescope, having so many eyes looking at the sky 24/7, we will see stuff that we have been missing over the years. About the addition of the network compared to what is done so far, one of the advantages is that first, it's a telescope that you can carry around, so people can basically, and set up very quickly. You will see tonight, if you come to the demo, you can basically move the telescope, press a button, it's aligned automatically, so people will be able to do this occultation much more easily. As you may know, when you do an occultation like this, and if there is always something wrong that will happen, Some tree will be exactly what you expect, not expecting them to be. Someone will turn on a light, and you will be. You have to move your telescope, so you could miss by a few minutes the occultation. With this telescope, you basically minimize this because it's an easy to align and easy to use. We will also have telescopes all around the world. We have sold telescope, in fact, in every continent so far. So that means that if there is an event which is observable, again in Oman and in Brazil, we will contact these specific observers, asking them to contribute to the observations. So that's the first thing. The reactivity is important too. It's a network. It's not only a telescope. So people being able to receive on their phone information about something happening right now, like a new comet being discovered, you're observing, and we get a request from the SETI Institute to observe this comet. You press yes, the observation are being taken by, let's make a big number, 400 people observe at the same time the same comet. We take all the observation of those comets, we stack them together, and we get the best picture of a comet. So the reactivity will also allow us to do some scientific investigation to react on events happening in the sky.
Okay. So your first question about the sample amount. The answer is we don't know because we don't have any sensor to know the amount of sample. So we will know it after we open the capsule. And actually, our target mass is just 0.1 gram, just like that. So if we have 0.1 gram, we can do all the sample analysis. But we hope we will have much more than that. Yes.
I have one more question. This is Karl Urban again. One more question concerning the sample return to Earth. So what are the main scientific objectives for the labs afterwards? What do they want to find out with the Ryugu samples on Earth?
Okay. Okay. So your question is, what is the main science goal? Yes. Sample, yes. So we want to study the organic matter on the Ryugu. So because actually we want to know the origin of life on the Earth, and we think Ryugu has original matter that became to life. So our main purpose is analysis of organic matter on the surface of Ryugu.
Yeah, just to complete, because with the analysis on the Earth, you can have a much more sophisticated analysis that you cannot have in the space. So bringing back the sample, you can do so detailed analysis on the small grain that will give us really a lot of information.
Hello, I'm Thomas Schumann, a freelance journalist from Denmark. I have two questions for Frank. The first question is with the Event Horizon telescope. You know, they used a lot of telescopes around the world to pinpoint one source and get an image together. Would that also be possible with Unistellar, that kind of science? And the second one is how freely can users of Unistellar just use it for their own purposes?
So I'm going to answer to the first question, the second question first. So if you get the telescope, you can do whatever you want with your telescope, of course, and observe whatever you want. In the app, we will have a list of targets that we recommend because they're beautiful, because they are interesting in the area of the sky that you can see. But you can also enter your own coordinate, Radek, and observe any part of the sky you want. So the data, to get the data, you will have to send it to us, and we send them back to you in the format that you can use to process, to do your own astrophotography or your own analysis as well. So you have access to your data. The second question was what was it?
It was, with the Event Horizon telescope
Ah,
that took
yeah.
the first picture of a black hole, I guess the technique is to use a lot of telescopes to get a bigger aperture. I guess
So-
would that be possible here as well?
So the Event Horizon is using is a radio array. So in this case, they can do they can combine the image by using techniques which are way more complex than what we're using, interferometry. We cannot do interferometry with this telescope. In this telescope, you basically will be able to combine the intensity, the images together to get a very good signal-to-noise image. We will be also, something important is that we are kind of standardizing also astronomy with this telescope. So we know how the telescope behave, we know the sensor, we know very well the flows of the sensor and how to correct them. So when people will send us observation of light curve, for instance, we'll be able to combine them and to get an excellent signal-to-noise light curve. So much better light curve that if you had multiple telescopes observing at slightly different wavelengths, slightly different filters, slightly different apertures. In this case, they're all identical, so it's easier to combine the data together.
All right, maybe one last question.
Hello again, Camille again from Sky and Telescope. So to repeat a question I had earlier, why would material move from the pole to the equator on the asteroid, such that like it's brighter on the equator?
Yeah, this is something that you have to come back to the history of the object. So these objects are considered rubble pile because they had the parent body and had a collision. And this rubble pile was an aggregation of this material of the fragment during the formation. So this is something that for the Yorp effect, when the objects rotate very rapidly, seems from numerical simulation that all the material go from the pole to the equator. And this has been confirmed with the Ryugu for the first time. So it was suspected to be the case for Bennu because we had the radar observation that was making hypotheses on this type of shape, but we didn't know about Ryugu because we were not able to have radar observation before. So this was really a very good confirmation.
So maybe you can explain what the Yorp effect is.
Yes, you can go with the temperature.
It's
Okay. Now, this is something that you have with the warming or with the temperature of the sun. You know, okay. So one of the ideas was that before Ryugu was probably rotating much more faster than today.
All right. Thanks to all the speakers for that excellent presentation, and thank you to everyone who participated. And we'll see you tomorrow at the same time for the third session of the press conference. Thank you.
Thank you. Thanks. I love that.
It's nice, huh? We would like to have, but
I would love to have one. I hope I'm going to have one day.
if you don't want to bring back, you
Thank
can
you.
give it to us.
All good? 20 years.
You want to give
What?
me? Okay. Can I take? Ah, wonderful.
Oh, yeah, it's true.
We know very well. Sì. Ok, va bene. Due cose, va bene. Sì, sì. Io devo parlare poi alla sessione, quindi proprio rapido.
Fammi mettere...
Ok.
I'm working closely with the science program of Deutschland. I wonder if we could just have sometime today.
Okay, I have a presentation this afternoon, but then if you come to the poster section, I will be around or today or tomorrow, all the day.
Particular poster?
There will be the poster section with the Ryugu and Bennu, because I am both in both missions, so I think if you are there around, it will be easy. Because yes. Yeah, it's so nice.